Okay, so it's a pleasure to have Baskın here at ROMER. He earned his BS in computer engineering from Nature in 2017, and during his undergraduate studies, he worked with me at Cologne Research Lab. And in 2019, he received a Master of Science in Computer Science from University of Southern California as a Fulbright grantee. Throughout his master's program, he engaged in research on decentralized multi-robot trajectory planning at the Automatic Coordinations of Teams Lab, advised by Professor Nora Ayanian. In 2023, Baskın completed his PhD in computer science at USC as an Annenberg Fellowship recipient. His doctoral research conducted under the mentorship of Gaurav Sukhatbey in the Robotic Embedded Systems Lab. Shortly thereafter, in the same year, he joined NVIDIA as a senior software engineer working on behavior planning for autonomous vehicles. Baskın's research interests encompass decentralized trajectory planning, control, and decision-making for multi-robot navigation. With that, I'd like to welcome Baskın back to ROMER/Kovan, and look forward to have his PhD study and share his results with us.
Thank you very much. Okay, so initially, I was planning to give like a more abstract talk. Then I realized that we have 2 hours allocated to us. So I have lots of math in the slides, so please don't be stated to interrupt me at any moment and ask questions. So yeah, today I will work on my research, mainly at USC, not related to NVIDIA, but I'm trying to push them in this direction as well, with some of these ideas from my PhD. Great. So yeah, I will mainly talk about my research that I have conducted for 6 years at USC, which was always on decentralized decision making in multiple systems, specifically for navigation, which makes it a bit easier compared to other decision making problems in which the problem space is more complicated. Great. All right. Maybe I should just get my mouse here. They actually taught me how to use this, but cool. Yeah, so today I will start with the motivation and I will define the problem that we are trying to solve in this research line. Basically, the problem is decision making for navigation. I will first talk about the existing approaches in this domain and talk about 2 different taxonomies of these approaches. The first one of them will be based on the deployment options. We will see centralized algorithms and decentralized algorithms. So the difference here is where we deploy these algorithms to make decisions. Then I will talk about another taxonomy in which I will be classifying these algorithms based on their planning horizons. So we will see 3 classes: long horizon algorithms, medium and short horizon algorithms, with qualitatively different properties. Then I will go over the solution that we have developed throughout these 6 years. Basically in 3 main titles, and finish with some concluding remarks, and I guess more importantly, some future research directions in which I will address some of the shortcomings in our approaches. Nice. Let's start with the motivation. Yeah, so basically decision making in for multi-robot navigation is a fundamental enabler for many real-world tasks, right? Like many of you probably know these application domains. We see these systems in common crowded spaces, for instance, in train stations, as autonomous patrol robots, for instance, or cleaning robots. We see them in traffic ways as autonomous vehicles. We see lots of applications in disaster zones. None of these problems are completely solved, but these are the application domains. We see lots of warehouse automation. And if your warehouse is not structured, if it is semi-structured or unstructured, then the problem gets considerably harder. If you have structured warehouses, you can do what Amazon is doing, right? Because you can control everything. But once you have humans in the space as well, navigation becomes harder. We see them on sidewalks as last-mile delivery robots, in food delivery or those kind of tasks. And then we see them in obviously battlefields as well. especially in the context of tactical reconnaissance. Right? And basically solving these decision-making problem for navigation, basically collision avoidance and deadlock avoidance, both of which I will exactly define, enables many real-world applications. And many of these problems are not solved. I would say none of them are solved actually. And then we are seeing progress slowly in this area. So the obstacles in these environments can be classified in many ways, but in this research line, we go for this specific taxonomy of obstacles, or objects in general. We first say that an object in this environment is either cooperative or not cooperative. Basically, these cooperative objects are all objects that we can directly control. So we decide the algorithm that they run, how they behave, what kind of sensors they have. And in the end, these robots are explicitly cooperating with each other in order not to collide with each other. And not cooperative objects are everything else, right? So it's like floor balls. And we further categorize not cooperative ones to static and dynamic ones. Static ones are objects that do not move, and dynamic ones are the ones that move in the environment. And we further categorize dynamic objects to interactive ones and not interactive ones. Now, interactive ones are all objects that move in the environment, but change their behavior based on what cooperative teammates are doing. Right? Like, for instance, I'm a human. If I walk in some way, if there's another human in that region, that human changes their behavior. Right? They might try to reproduce itself, or some. Sorry. Oh, it's just an echo. Sorry. Yeah, so interactive objects may be changing their behavior to avoid collisions as well, or in some adversarial scenarios, they might actually try to actively pursue us and then hit us as well, right? Or it can be anything else. And not interactive ones are all objects that do not change their behavior depending on what we do unless we collide, right? So this can be some ballistic motion or anything that actually moves with laws of physics or any system that doesn't respond to us explicitly, right? And in the end of this talk, we will be avoiding all objects in this taxonomy, but we will be handling each object differently based on the nature of their movements. Right? Cool. Yeah. So first, let's see the existing approaches, existing approaches. And then, yeah, let's try to create their taxonomies. We will first see the deployment options. And as I said in the beginning, we have two ones. We have the centralized algorithms. And the idea of the centralized algorithms is that we have a multi-robot system. We want to plan trajectories or make decisions for their navigation. In these centralized approaches, there is a centralized computing system, which can be a single machine or a cloud or a cluster or whatever, right? In which we make decisions for all robots. Now, in these approaches, plans are communicated back to the robots for them to execute using their onboard control. In centralized approaches, we generally see global completeness and optimality guarantees because there is a centralized single algorithm that decides the movements of every robot in the environment, because of which we can go for completeness and optimality or those theoretical stuff. And the reasons are with the power of centralized computers. And generally, these approaches utilize the complete environment knowledge. They assume that we know the environment beforehand, which is not realistic in all scenarios. And generally, there is mild time limits. There is no real-time requirement in general. Obviously, there are approaches that require them as well, but it's in general trend. The problems with these approaches are if you have, for instance, communication problems, right? Which is the case in many real-world applications. If you are in the military context, you can never rely on communication. Even if you are not in the military context, communication is best, right? That's how the modern communication systems work. The second one is, if you don't know the environment beforehand, then you need to have some capability of building local environment representations and then sending them into this centralized computing system so that it can do the centralized decision-making for you, which actually requires your communication requirements considerably. And if you have communication problems, then you will not be able to do that, right? And also we have low reactivity to new information and imperfect trajectory tracking because of the same exact reason. If you move decision making to a centralized system, you need to wait for the centralized system to make decisions for you. And if you have communication problems again, even if you don't have communication problems, you will always have some delays. You cannot be real time. So the decentralized approaches are a solution for these problems, but obviously we are losing some of the properties. So the idea here is that each robot has the onboard autonomy to make decisions for itself. These robots can communicate with each other using inter-robot communication, whatever infrastructure to have. These approaches can work with locally maintained environment representations. You don't need to have a global map of the environment, and robots can simply create a local environment representation around themselves and then make decisions with that. But obviously, and then we can do real-time decision making as well because everything is on. But what we are losing here is global completeness and automatic guarantees, because you cannot expect the robots to maintain the full environment representation on board because of storage and memory limits. And also, since we need to do real-time decision making, you cannot have global completeness and automatic guarantees with time limits, because multi-robot navigation problem is can be hard. Right? So basically, these are two alternative ways of thinking about this problem. But again, in the end of this talk, we will actually not see these as alternatives, but we will try to merge them together and then get their powers in a useful way. So yeah, we'll see. Great. Now let's look at the planning horizon taxonomy. So the first set of approaches are these long horizon approaches, in which these algorithms make decisions for the full navigation path, which means that given start positions and goal positions, we plan full trajectories or make decisions for the full task. And these approaches generally go for complex guarantees, because of which they are generally centrally deployed. Right? Some of these approaches go for kinematic feasibility. Here I use kinematic feasibility for collision avoidance, and sometimes it is used as like not constant forces, but used to have some dynamics. But yeah, kinematic feasibility just means collision avoidance, or they can go for dynamic feasibility, which means that you both avoid collisions and your plans are dynamically feasible by the to execute by the underlying system, whichever that might be, it's a drone or something, right? These approaches are generally not real time because the planning horizon may grow to infinity. If you can grow to infinity, you can never be real time in the worst case. And if you require dynamic feasibility, even if your planning horizon is short, these approaches are still not real time. Like for instance, this approach runs for this particular case for in like 200 seconds or something. So you basically wait for 200 seconds for it to produce the plans, you give them to the robots, and then they execute. Again, as I said before, these approaches are generally centrally deployed because global environment presentation is needed for long horizon decision making, and the approaches are computationally heavy. And generally, we don't see dynamic obstacle avoidance in these approaches because dynamic obstacles, by their nature, are transient. Right? Like you don't know where they will be or if they will exist at all before starting navigation. Right? Unless there is a very systematic thing going on, which is better rate. On the other end of the spectrum, we have the short horizon approaches. So these approaches, given the local environment representation around each robot, compute only next action to execute, right? Whatever that action is in your underlying system. Doesn't matter. There are some robots that are moving around. Not that important, just some videos running around. That's some robots. So the idea here is, since they only compute next action to execute, you can actually run these approaches in a very high frequency. So we see lots of safety barrier certificate or control barrier function-based approaches here. Many reinforcement learning or learning-based approaches fall in this category as well. And the idea here is, instead of planning for the full navigation task, you plan for the next action, execute the action, and now you have a new environment. You recompute and then keep doing it again, right? Because of since you are doing one-step consideration of your actions, these approaches allow high-frequency execution, and they can be run on board as well. They allow decentralized deployment because you can put these approaches actually on robots and then run them in decentralized fashion. They allow integration of new information because you can run them on board. Generally, we see dynamic feasibility, not in the cases of some RL-based approaches, but if you are doing some pure control, you see dynamic feasibility. But the problem of these approaches is that robots actually deadlock in the environment. And what I mean by deadlock is, for instance, you go towards a V-shaped obstacle. If your only goal is to avoid collisions, you just go to the corner of the V-shape and then get stuck there. And from the perspective of the algorithm, you are successful because you are avoiding collisions, but not moving at all avoids collisions as well, right? And since you are not considering the long-term effects of your actions, you generate that. Learning-based approaches try to circumvent this issue. You try to learn the long horizon effects of your single actions. But obviously, as long as you are looking at the single action, there will always be cases in which you will deadlock because the problem is empty part, because otherwise it would be empty. Great. So in between long and short, we have these approaches that we call great. Great. So medium horizon approaches are in between long horizon and short horizon, and these approaches, the robots make decisions to reach intermediate goals, not the next step, not the full navigation task, but to reach intermediate goals. Typically, we see planning for next 10 seconds. We see a distributed horizon execution, which means that we plan for next 10 seconds, execute for 100 milliseconds, and then they plan from scratch. They also allow onboard real-time execution, but at a lower frequency compared to the short horizon ones. They also allow centralized deployment. They also allow integration of new information, and similar to the short horizon ones, they also go for dynamic feasibility. But obviously, the catch here is that you need like more hardware compared to the short horizon ones. So in the main chunk of this talk, I will be talking about medium horizon approaches and our developments. Both of them are part of some of our algorithms. But in the end, again, I will make peace between these long, short, and medium horizon ones and try to merge them together in a single stack to actually use to actually get the benefits of each one of them. So yeah, let's look at our solution and then how we are trying to solve this multi-robot cooperative navigation problem. And here I say cooperative because we can control some of the robots while there are some objects that we cannot control. The first one is a very specific method that we have to handle some problems that stems from asynchronous learning, which is a very detailed problem. I will start from that because it will be important for later. So with research line, we use separating plane constraints for interval collision avoidance. So these approaches, the first one of them started from Max Vegas group at Stanford about 6 years ago, in which they use basically buffer border cells for navigation. So the idea here is this. So let's say that we have these four robots, A, B, C, and D. Just unmute here if someone asks a question. We have these four robots, A, B, C, and D, with their corresponding pole positions. What these algorithms do is that they first partition the position space with separating hierarchies, perhaps something like this. In the case of buffer Borneo cells, these are actually the Borneo diagram of the positions of each robot. You can go for generalized Borneo as well. We go for spectacular machines, which I will define. Then, each of these robots plan trajectories that are fully or partially contained in their cells. Maybe something like this. And then these robots execute these plans for a short duration, which actually changes your partitioning, and then you replan from scratch, right? So as the time progresses, you get closer and closer to your goal position, but you are always contained within your own cell in every planning iteration, right? So this is the general idea. But there's a problem with these approaches, which is about like the centralized deployment. So these are the centralized algorithms. Each of these robots can compute their own cell in the environment without any communication with others, right? Assuming you can sense their shapes and positions, which actually allows A to plan for itself without ever communicating with others, right? But the problem with decentralized deployment is that these robots are not synchronized, right? They start and end planning at different times because there is no synchronization. Planning takes different duration in each planning iteration because everything, like nothing is deterministic, which actually causes a problem that we call hyperplane mismatch, which is something like this. So let's say that we have these two robots, A and B, and now at this moment, robot A decided to plan, right? It computes this separating hyperplane, and then starts a planning run to actually stay in this side of the hyperplane. But while planning, the robot is actually still moving, right? It changes its position a bit, and B moves as well in the same direction. And some time in the future, A finishes planning, and now A is constrained by this hyperplane, right? Now in the future, we know that A will be in this side of the hyperplane, but there's nothing about B. Then B, like robots keep moving, A is within itself, and maybe like we were lucky and then they did not collide. Now maybe B starts planning, it computes the hyperplane, right, which are not matching with each other. But now the robots are still moving until B finishes planning. So they keep moving, and sometime in the future, now B is constrained as well, but these spaces are actually intersecting with each other, right? So if we are not lucky, they can just like go on and collide with each other. So this is a problem that we call hyperplane mismatch. Depending on how fast you are planning, this mismatch increases or decreases. If you are planning in 1 millisecond, probably it's not a problem. But if you are planning in 100 milliseconds, then you will see more and more mismatch. And if the robots are close to each other, imagine you have like thousands of robots navigating with each other, you will definitely see this problem. Right? So in this first work, we try to address this problem while still staying within the realm of separating hyperplanes. So we define a concept that we call DSHT, or discretized separating hyperplane trajectory, which is basically a trajectory of separate hyperplanes between two moving bodies, discretized at high resolution, something like this. So let's say that we have two robots, blue and yellow, and they are moving. And at any instant of time, you can compute a separate hyperplane between them. And this trajectory of hyperplanes between them, we call DSHT, discretized at fine resolution. If you can synchronize time between these two moving bodies, which is possible with many protocols, right? Both of these robots can compute the same exact trajectory without any communication, right? Then we use these DSHTs as constraints instead of separating hyperplanes, and this is how we use them. So let's say that Hij is the separating hyperplane trajectory between robots I and J. At any point of time, these robots I and J are constrained by a different interval of this hyperplane trajectory. And basically what we do is we make sure that these intervals always intersect, which means that these robots share a constrained hyperplane at all times. And this is how we do it specifically. So each robot I stores tail time point variable Tij for each other robot J, which is always less than or equal to current time. If any point of time robot I starts planning, it constrains itself against other robots using all hyperplanes from Tij all the way to T current. Okay, let me just for it. So it's confusing because always confusing for me as well. So let's say that so this is the Tij, this is the specific point, that time variable that blue robot stores for yellow robot, right? So if this moment the blue robot starts planning, it uses all hyperplanes from here all the way to the end. And this is the same for yellow as well. The yellow uses all hyperplanes from here to the end.
Baskın, a little bit lost here.
Yeah. Yeah. So let's say we have two robots, right? And they're moving like this. Let's show there as well. Let's see. So now, let's say these two robots are here and here. You can compare the weight hyperplane between them. Right? It's one hyperplane. And they keep moving. You can compute another one. You can compute another one, right? And what's the trajectory? It's trajectory is a function of time, you know. At any point of time, this hyperplane can be computed. And then I call this trajectory of hyperplanes, which is not living in 3D space, but in space of hyperplanes, the DSHT. Right, so this basically, you can think of it as not a trajectory, but let's say it's a sequence, right? Okay. Sequence of hyperplanes that we compute at every time step between two moving bodies. Nice. So each of these robots will use an interval of these hyperplanes as constraints during the streaming. They will try to be in the safe side of each of these hyperplanes. Now what we do is we make sure that these intervals always intersect, which means that at any point of time, each pair of robots share a constraint hyperplane. And these are the specifics, maybe not the important, but this is general. Does that make sense? Okay. But the problem here is if you do it like this, Tij will actually start from 0, and then we'll keep using all trajectories constraint, and then we'll get over the constraint more and more, right? So what we do is we update these Tijs based on a very specific thing. And this is how it goes. So let's say that robot J plans successfully on a planning iteration that started time tau, which means that robot J used hyperplanes starting from some time before tau all the way to time tau. Right? It makes sense because robot J uses everything from TGI to the current time. And at the time that planning started, the current time was tau. So we know that we use the hyperplane at time tau and some hyperplanes before as well. From this point forward, we know that first robot J is currently constrained by this hyperplane at time tau. By the way, HGI and HIG are equal because it's the same exact hyperplane trajectory. And this is more important. There can be no case in the future at which robot J is constrained by a hyperplane before tau. So tau is here, TGI was here, this is the current time. In the future, there can be no case that robot J is constrained before hyperplane at time tau, at which it is also not constrained by the hyperplane at tau. Which means that we know that we are currently constrained by tau. In the future, if we are constrained anything before tau, we will be constrained by tau as well. This means that tau will always be there, and then we can forget hyperplanes before tau. And then we call this constraint discarding. After the moment J plans successfully, all robots in the environment can set their TIGs to tau, because they don't need to be constrained before hyperplanes before tau. Does it make sense? This is the key thing of this idea. And then this makes sure that at any point of time, each pair of robots share a constraint hyperplane, and we are also minimally conservative in this domain, because if we set Tij to anything more than tau, we cannot ensure collision avoidance. And if we set anything before tau, we are actually using unnecessary constraints. So yeah, we have a method that we call over-constraining and constraint discarding, which basically, this is a very simple idea. We assume that the communication medium we use is best effort, which is what all communication mediums are these days, in which messages may get lost, reordered, or delayed. So it's like internet maybe. So as I said, whenever robot J plans successfully, it broadcasts the time point as well as this ID that it successfully planned at this particular time instant. And all other robots J that receive that message update their time points. If they cannot get that message, they don't update their time points, which means that they over-constrain themselves against me, but they still make sure that they are still sure that we will always share a constraint hyperplane, because if you don't update your time point to tau, it becomes something before tau, which means that whenever you plan in the future, you will use the hyperplane tau as well, right? So this is the general idea. So this makes sure that first, initially we always share a constraint hyperplane. If you ever update your hyperplane trajectory intervals, you do so in a way that makes sure that we keep sharing hyperplanes. And if you don't update them, we by default keep sharing hyperplanes. Right? So this makes sure that in an inductive way, we always share that. So from the perspective of robot J, something like that, saying that it knows that some other robot I planned at some time instant, and it doesn't know if it plans successfully ever again. So this is the way of thinking that it's used. Right. So yeah, this is basically the minimally constraining thing that you can do while also ensuring that you'll avoid problems.
So in this case, there is no common time.
There is common time. So we assume that there is time synchronization, which you can do with some protocols. And the problem is that sometimes with Bask, there should also be sensor synchronization. So when you sense them, they can sense you as well, but it's not reality. You generate 1-2 millisecond delay or something. We omit that delay. That's the problem as well. But basically, delays that we are aiming, targeting here are delays in the order of 100 or 200 milliseconds. So that's how I justify it. Cool. Great. So now, this is just a constraint generation method. Now we will see how we use them in an actual planning algorithm. Right. So in the second part of this talk, okay. I will talk about a medium horizon decision making algorithm, which is decentralized, that we developed for multi-robot collision avoidance. And this algorithm actually avoids all kinds of obstacles in our initial taxonomy. We can avoid static obstacles, dynamic obstacles, which can be interactive, as well as teammates that are running asynchronous. Great. Cool. So yeah, this is these are the videos from the algorithm. You'll see them in more detail later. So the planning setup is we deploy this algorithm in a decentralized fashion. Each robot plans for itself using onboard capabilities. We assume that each robot creates a local environment representation around itself, which it uses during planning as well. We do receding horizon planning because we are medium horizon. We plan for 2 to 10 seconds and then execute for 100 milliseconds or something like that, and then replan from scratch. We go for dynamic feasibility. I will define exactly what it means. And I will be describing the algorithm from the perspective of a single robot in the environment. So let's go back to our taxonomy now, and then let's talk about how we are going to represent these objects in the environment. For cooperative teammates, we'll use DSHDs that I just defined. We assume that each robot in the environment tracks DSHDs in a parallel thread for each other robot in the environment, and then keeps updating them. And now we will see how we present other objects. For static objects, so basically OI is all static objects sensed by robot I. We assume that we can sense its shape, which is Pij, and we assume it to be convex in separative sense. Then we assume that we have the existence probabilities of each of these objects in the environment. So many data structures like conjugates or octaves store the objects in this form. Basically, you have these boxes that are occupied with some probabilities, which actually exactly maps to this definition, and we use octaves in the implementation. For dynamic objects, definition is a bit more involved. Now, for each dynamic object J sensed by robot I, we assume that we know its current position in whatever coordinate frame. We assume that we know its convex shape. Basically, you can just sense the convex shape and then attach the coordinate frame to anywhere in that shape, or it can be outside the geometry. And then we have a number of predicted behavior models I will define shortly. So BIJK is the K behavior model of J dynamic obstacle sensed by I robot, right? And then we have their realization probabilities, PIJK dynamic, which means that, for instance, if PIJK1 is 0.1, it means that we believe that this particular obstacle, this particular dynamic obstacle, uses the first behavior model with 0.1 probability, right? So we assume that we have a prediction system that actually outputs these models like this, and then our probabilities are within the probability sequence. Now let me define what a behavior model is. So behavior model is a tuple of two things: a movement model and an interaction model. So movement model describes the intent of a dynamic obstacle. It is a function from dynamic obstacle's position to its velocity, right? You can actually make this more abstract. You can say it is a function from state to action, but we go for position and velocity so that the underlying geometric operations becomes faster, but we can basically define in any way we like. Now, in our case, it's a function from position to velocity. It's basically a vector field. Basically tells if I put this dynamic obstacle anywhere in the world, what we want to do. Right? It's a policy describing this behavior. Interaction model is another function that defines how this dynamic obstacle interacts with the planning robot. It has four inputs: the position of the dynamic obstacle, the desired velocity of the dynamic obstacle, which comes from the move model, the current position of our robot, and current velocity of our robot. Given this, it gives us the actual velocity of the dynamic obstacle. It's something like this. Let's say we have a dynamic obstacle. I put dynamic obstacle somewhere in the world. I know that it desires to go to some direction from the move model. Right? Now, as a robot, I am here, and I am moving in this direction. But the question is, given this information, how much will this dynamic obstacle change its desired velocity? Right? So the interaction model tries to answer that problem in a very simple sense. Again, you can define this as state action, and the actual action form. But we go for position velocity, so that like geometry is easier. Like for instance, this can be a move model. If it wants to go some particular direction, it can be something called attractive, rotating, or anything in general. Like these are very simple ones. Like if you are driving a car, you might have a vector field pointing towards the lane that you are going, or things like that. And for the interaction, it can be a impulsive interaction. Maybe like if we are very close to the dynamic obstacle, it might try to get away from us. Or if it's actively trying to hit us, it can be attractive as well. You can try to avoid that as well. But this is the general idea. Great. So now we know how we represent each object. For cooperative teammates, we have these HTs. For static obstacles, we have their shapes and existence probabilities, which we assume are independent from each other. And for dynamic obstacles, we have their shapes, positions, which are actually the same thing. You can attach the position to anywhere. And their behavior model, each of which containing a moment interaction model, and their realization probabilities. So this is the representation. Let's see it thoroughly. So this is our robot, the green one. The yellow ones are the teammates. And for each one of them, we actually, obviously, like these are pictograms, not the exact things. For each of them, we maintain the DSHT. For each static obstacle, we have their existence probabilities, which is like octaves and octaves are giving that to us. And for each dynamic obstacle, we have movement and interaction model, which is a behavior model with their corresponding realization probabilities. And the probabilities are in the probability syntax. They all add to 1 here, but they don't work if you have something residual going on. Great, so this is the representation. Let's see what the problem is that we are trying to solve. The problem is basically, we assume that each robot R in the environment has a desired trajectory that it needs to follow. So this desired trajectory can be a single goal position if you want that robot to go to achieve that. It's basically a constant function. It can be a full trajectory that might come from an upper level planner. And yeah, those are the only two options that I can think of. So we can actually, we may need to do full navigation from start to goal without any guidance, but we also accept guidance as well. We assume that our robots are differentially flat in their position outputs, which basically means that given the system equation of that particular system or particular robot that you have, the states and actions for the inputs can be expressed as in terms of output trajectories and the finite number of trajectories, finite number of derivatives of this output trajectory. And since we assume we are differentially flat in position, this means that if I give you position, velocity, acceleration, jerk, snap, so on, like whatever you need, can you give me the actual states and inputs of this system? So many systems, including quadrotors, cars, many omnidirectional robots are differentially flat. So this is like not a useless abstraction; it's a useful one for our use case. Now, so if your system is differentially flat, if you can impose continuity of the output trajectory up to some degree that's required by your system, if you can bound the derivative magnitudes of your system, then you'll know that this particular plan that we produce will be dynamically feasible. Right? And then we assume that there is a state estimator that estimates the kth derivative, PIK self, of the system's position for all the required degrees up to degree CR. Right? So these are the assumptions. So we know our current state in our abstraction. We know the desired trajectory. Give me the next trajectory to execute, which I know that will be dynamically feasible because I assume that the system is differentially flat, then I know these numbers. Right? Yeah. Great. So our planner is very classical in its design. So many planners go with his design. There is a goal selection step, which actually selects a goal to plan towards. In our case, since we have a desired trajectory, we use that desired trajectory during goal selection. Then we will do discrete search using cross-algebraic A-star to find a spatial temporal path towards a selected goal position. Then we will have the trajectory optimizer, which will be solving a convex quadratic program to fit a piecewise Bezier curve to this discrete search output, which will be our next trajectory. We will be running that trajectory for a very short duration and then run everything from scratch. Right. This is the general formulation. Great. So let's start with the goal selection. So this is, let's say, this is our desired trajectory, which doesn't have to be collision free, might collide with anything in the environment. What we do is we have a parameter that we call tau I, which is desired time horizon. T tilde is the current time. So we are looking at the position on the desired trajectory that is one planning horizon away from the current time. And then we increase it minimally so that the robot is collision-free against all static obstacles in the environment. You can use some probability thresholds as well, but here let's assume that it's 0. So basically, we find the smallest time point that's one planning horizon away from the current time, at which a robot is collision-free. Right. So this is the cost. And then in the rest of the algorithm, we will try to find a trajectory that drives this robot towards its goal position. As time progresses, our selected goal will progress as well. Now we will try to navigate further and further in the desired trajectory. Great. So in the discrete search, as I said, we compute a spatial temporal path to the goal position. We do next ordered multi-objective search. Basically, we will have 6 objectives in our search, and these 6 objectives are vectors. Now we order these vectors in a lexicographical order, which means that we'll first minimize the first cost term, and then among solutions that minimize the first one, we'll minimize the second one, and then we go on like that, right? And then I will define the exact cost terms. So the states of our search tree has 6 components in total. The position, time, and direction. So basically put a grid on the environment that is oriented along the current velocity of the robot. So it doesn't have to do unnecessary turns in the beginning. And then we do search on this grid, right? But this grid is actually aligned, oriented in the road. And this direction is the direction in that particular grid. Position and time are I guess simple. And for each type of objects in the environment, which are static objects, dynamic objects, and cooperative teammates, we have 3 sets for each state. The first one is colliding static obstacles. So basically, for each state X in our search tree, we store all static obstacles that the robot collides while traversing the state sequence from all the way X1, which is the root state, the current state, to the X. Right? For dynamic obstacles, we store each behavior model position pair, which means that if Bijk and Pijk is xt, this means that dynamic obstacle J, moving according to K, stands for robot I, does not collide with the robot traversing the state sequence from X1 to X, and the dynamic obstacle ends up at this position Pijk dynamic. So we do this for every dynamic obstacle and for every behavior model of each dynamic obstacle for each state. It's like a very memory problem, but it's not a problem in practice because the problem is not that hard actually. And I will define how we actually maintain these sets. The last one is XH. These are the violated DSH type claims. So basically, while going from X1 all the way to X, which means that we actually traverse some positions on the way, we'll be violating some hyperplanes from all of the DSHDs. We store them all here in XH set. And again, we do this for every hyperplane of every DSHD, of every teammate for each state in the search tree. Right. So now let's see what our actions are. We have 3 actions. Forward ST moves the robot forward in its current direction on the grid with speed S for time t. Right. So the position and time updates are pretty simple. Talking about the set of obstacles first. So let's say that X plus is a new state after applying this action, and X is the current state. Right. We basically sweep the shape of the robot along from XP to X plus P in a straight way, which actually becomes swept vision. Then we query our OpT to see if this swept shape collides with any of the obstacles in the environment. So here, like, we have some details. We do first to like world phase check, just the bounding boxes. Then we do actual check against swept space with number of phase collision check, and then update our all set as a set of static obstacles that we collide so far, and the new ones that we collide along the way in this last state expansion. For dynamic obstacles, we actually run the interaction models and moment models. So this is how we do it. So let's say that BIJK dynamic is an XT, which means that this particular dynamic obstacle J, moving according to Kate behavior model, did not collide with our robot from start state all the way to this state, and it ended up here, right? So let's say this is our dynamic obstacle, this is our robot, and we are currently at X dot P. And now our robot wants to execute V robot, which we can compute from S and T and the direction. And this is the current position of dynamic obstacle. We first run the movement model and get from the movement model the desired velocity of the dynamic obstacle. Then we run the interaction model, to which we feed the current position, the desired velocity, I forgot about JK here, the current position of the robot, and the execute velocity of the robot during the state expansion. We get the actual velocity, and then we sweep these shapes for one step, like just simple further integration. And then we check whether these two swept regions intersect with each other. If they intersect with each other and they're colliding, we do not add this behavior model and new position to the new state. If they do not, we add it. So this is how we maintain everything. For the initial state, we initialize them to behavior models of all dynamic obstacles that not initially collide with our initial state. So this way we actually maintain it. All right, so this is how we do state propagation. Then we compute collision probabilities. So, okay, it's fine. So for each state in our search tree, we compute the probability of colliding with static obstacles, or compute the probability of colliding with dynamic obstacles, right? So let's say that CS this trajectory, I can just so this is the event of colliding with this particular trajectory while following it. The nice thing is, event of not colliding is naturally recursive. So not colliding with a prefix and the corresponding suffix of a trajectory can be written as not colliding in the prefix and not colliding in the suffix, right? And if you do a simple Bayes rule, not colliding in prefix and suffix is equal to not colliding in prefix times not colliding in suffix, given that we have not collided in the prefix. So during this state expansion, for each state, we compute these probabilities. The nice thing is you can get this from your parent state recursively. Only challenge is computing this conditional term. Okay, and yeah, this is like the pictorial way, and this is the symbolic way, which is the exact same thing. Let me just define how we compute these properties. So given that we have not collided in the prefix, for instance, for static obstacles, means that any static obstacle that collides with the prefix does not exist, right? That's our premise. Because if it existed, we wouldn't have this premise here, right? So we know that those obstacles not exist. Then the probability of not colliding in the corresponding suffix is the probability of those static obstacles that collide with this part, but not with this part, not existing. Something like this. So we have a search tree. So these A, B, C, and C, D, and E are obstacles, and X1 is our current state. We do state expansion. We have the sweeps. So now let's say that we want to compute the probability of not colliding in the suffix, given that we have not collided in the green part. So given that we have not collided in the green part, means that A, B, C, and D doesn't exist, right? We know that. Because of which, we can compute the probability of not colliding in the suffix as the probability of obstacle E not existing, right? So this is how we do what we do for each state. Then we do a similar thing for dynamic obstacles as well, but in the end, for each state in our search tree, we compute the probability of colliding the static obstacle or with the dynamic obstacle. Great. So now let's talk about our 6 costs. We are doing next ordered multi-objective search. We have 6 cost terms, one for each type of obstacle, static, dynamic obstacle, and teammates. And then we have other performance metrics that we call distance, duration, and rotation. So by the way, I'm not sure if I'm okay. Okay. All right. So let me just finish this search part, and I will stop there. Maybe I can show you some videos. Okay. Then we interpolate these collision probabilities. So what we do during search is that we compute the collision probability for each state, but we don't know what's going to happen in between. We interpolate them. We do the same for dynamic obstacles as well. And for the cooperative teammates, we interpolate the number of violated PSH lanes. Then we use them in a cost term. Static obstacle avoidance cost term is the area between this interpolation. The same for dynamic obstacles. Same for teammates. For distance, we have total distance. We have total duration. For total duration, and then we have number of rotations. And then we do the search. And what search does is, it first minimizes J-static, which means that we minimize the cumulative collision probability with static obstacles. And among the solutions that minimize that, we minimize dynamic one, and then teammates and so on. Right? So the collision avoidance is primary, and other performance metrics are secondary cost terms. Among collision avoidance against different types of obstacles, we first minimize static, and then dynamic, and then teammates. And then we have heuristics, all of which are admissible. And then we do time search, which means that we limit the total duration of the search because we need to be real time. But the nice thing is, whenever we cut the search off, we will get lots of candidate solutions because we have this action that we call reach goal, which connects every expanded state to the goal state, so we can directly minimize that. Great. Then we feed these to phase optimization to smoothen it, and then smooth it, and then make it dynamically feasible. I will just skip all of this stuff and just jump to the end. Yeah, I really planned for 2 hours. Okay. Great. So yeah, let me just talk about the idea of this thing. What we try to do here is, like in an abstract sense, and that's what many approaches are doing these days. Then we first select the goal position, and then we do discrete search. And the idea of discrete search is to define the homotopy class of our final trajectory. And during optimization, we generate the final dynamic feasible trajectory that is contained within the homotopy class of this discrete trajectory count. Right? This is the general idea. And the specifics are very specific. Yeah, let me show you this video. Great. So this is a single robot case. We have like many dynamic obstacles, highly cluttered. And we are basically navigating with a problem here. So the planning duration is like 50 milliseconds here in each iteration. We execute each plan for 100 milliseconds. We actually have 3 predictors as well. We predict the movement of each dynamic obstacle in real time here. But we assume that we can sense dynamic obstacles and their shapes, which is a big assumption. Now we do the same thing for this is like the case. Yeah, for these moves. And then we have a case, again, obstacles are coming towards us. Spoiler, it will avoid them. I won't show them. Great. Now we have the multi-robot case. I'll just skip this. Another multi-robot case, it's a bit fuller, but the visualizer is here because of number of obstacles. Yeah, now we have the robots here, and they are completing DSHTs, as well as predicting dynamic obstacles and then avoiding them. Great. And then we have some real robot experiments as well. These are like with basic license and Python. So 6 robots are acting as dynamic obstacles here, and every one is navigating among them. What's this? Yeah, we have the multi-robot case as well, with dynamic obstacles. And then we have a comparison. So these were all the algorithms once we wrote this paper. And then we looked at the comparisons between them, and then chose the ones that were the root of this tag. Let's say some tag, but yeah, we compared against these 3 and then showed that we are better than everything out there. Great. So now I need 30 more minutes, but I will just like fast track everything. So maybe I can talk about this. So in the end of all of this hassle, what did we achieve? So we have this like medium horizon algorithm with which we can avoid static obstacles, dynamic obstacles, and asynchronous playing teammates. We can handle communication problems, and it's the best approach currently out there in this domain. But we still don't have any complete and global operative guarantees. We still don't have collision avoidance insurance, and this is because the planner might fail sometimes. So I couldn't show the table, but we have a success rate, and success rate is not 100% in every scenario, right? So now in this last work, we are trying to attack these problems as well, how we can do that. And then we have some design challenges. I will not go into details, like we have limited onboard compute memory and things like that. Communication is imperfect. We have imperfect prior knowledge. Controllers are imperfect. And then we need high reactivity. And on top of that, we need minimal sensing because we can't actually sense everything. Right? So these were our major design challenges. And this is the design. So what we do here is, initially I defined long, medium, and short horizon approaches. And then here we try to combine them all together. So medium and short horizon ones live on board. So this is the onboard side. And there is a centralized long horizon that runs on demand whenever you have communication to centralized system. But if not, a medium horizon takes care of everything. What medium horizon does is it gets desired trajectory as we defined in the previous work, and tries to follow it as close as possible by generating reference trajectories. We feed that to robot control, and then we have the short horizon one, which gets desired control and then makes it safe. So this design actually makes sure that every action that we send to the actuators are safe in every iteration, which actually solves medium horizon approach failing. And whenever we have communication, we go to long horizon for optimality and completeness. It's the general idea. Then we go into details of each one of them. This is the medium horizon. Now we implement this for simulated quarter flight. For long horizon, we just do kinematic A*. For medium horizon, we use our algorithm. For short horizon, we use control barrier function-based approach. And then run it with full dynamics in Gazebo rotor simulator. The video is a bit big. Okay, that's fine. PowerPoint not working as far. That's fine. You'll see some cloud cross flying and not colliding. And then we have a long hour run as well. So we run this algorithm for 8 hours without any interruption, which is here, 8 hours long, without any collisions and deadlocks. Obviously, we will not wash them out. YouTube is great. So yeah, let me just talk about this particular thing. It's the most important thing of this particular work. So here we have 4 different environments: a forest environment with 400 dynamic obstacles, forest with no dynamic obstacles, a maze environment, which actually requires you to have long horizon decision making with 210 no dynamic obstacles. Now we use every combination of these approaches: short horizon only, medium horizon only, long horizon only, medium and short, long and short, long and medium, and long, medium and short, which is what we are proposing, right? And then we have this deadlock rate, number of robots at deadlock, and the collision rate among the tasks. And whenever we have zero collision, we call it successful, right? If you look at the results, like for instance, in this particular case, medium and short is enough, but long, medium, and short is okay as well. But in this particular case, only thing that works is long, medium, and short because we are in a maze-like environment. So these are the main things that we get. First one is enforcing safety of each executed action is essential. We get this property from the short horizon one, and every successful combination contains a short horizon one, right? So what we see here is basically whatever you send your actuators, you need to make sure that they are safe for each action that you send. That's the first thing. The second one is dynamic obstacles create need for local data resolution. So local data resolution is provided by the medium horizon decision maker. And in cases with no dynamic obstacles, long and short is enough. So you don't need things like that I described, right? But whenever you have dynamic obstacles, you need those approaches. Third is global data resolution requires global reasoning. So global data resolution is required in maze-like environments. And every successful case in maze-like environment contains the long horizon ones. And this is the most important. No approach is sufficient by itself, and all is required for effectiveness in all scenarios. So basically, you need all of them. So yeah, this is the idea. The research, let's talk about future directions of it, and then I will just finish the presentation. The first direction is modeling worst-case dynamic object behavior. So we assume that we have this proper distribution across behavior models, but how would you even know that those behavior models reflect the reality, right? So here, an idea can be maybe having a reachability-based residual model, in which, with some probability, this dynamic obstacle will move according to something outside of these things, but we don't know what it is yet. So you can make the reachability analysis and then preparing decision making as well. We don't model uncertainty of state transition during search. We assume that if you execute some velocity, it will be realized by the robot, but it's not reality. That's a projection as well. The short horizon thing that we implemented do not model interactivity, which is actually causing problems sometimes. I don't have time to discuss the limits of the design, but yeah, it's a limit. We don't have full stack integration. We assume that we can sense where obstacles are, where robots are. We assume that we can distinguish different types of objects, which are like really hard problems. So full stack integration and seeing how these would behave, which I assume would be pretty bad, is a thing. Explicit plan communication, we don't have that. We just use PSHT maintenance communication, but you can also need to communicate your plans explicitly, which some methods like robust Mader or Mader are doing these days. But doing it in a controlled way, in which you don't actually assume something about communication, it's still challenging still. And as you said, the exact same question, modeling interdynamic obstacle interactions and interactions of dynamic obstacles of multiple robots is an area of research as well. Great, so yeah, thank you very much. That's basically it. So these are the related publications if you want to check them. So yeah, thank you.